This video is for topic 7.12, Common Ion Effect. And the objective for this topic is to identify the solubility of a salt and/or the value of Ksp for the salt based on the concentration of a common ion already present in solution. So this is one of the effects of Le Chatelier's principle. And so what we're going to look at is if we dissolve or attempt to dissolve a salt in not water, or so it's probably a solution of water and some other salt, where there's a common ion, either the anion or the cation, between the salt we're attempting to dissolve and the one that's already existing in solution, it's going to be less soluble. And so what we're looking at here is essentially Le Chatelier says that some of the product is already there. So if some of the product ion already exists, less of the solid is going to turn into the aqueous ions because some of the aqueous ion is already there. We're going to be able to make an approximation to simplify some of our calculations, but we're going to attack this just like we would most any other equilibrium or specifically a solubility problem. And so we're going to use our equilibrium expressions and we're going to use our ice tables to help us organize our information and look at the effect of common ions.
So in this problem, we're looking at trying to dissolve silver chloride in a 0.55 molar solution of sodium chloride. And we want to know how much silver chloride will actually dissolve. So what we need to recognize is that our solution already contains sodium ions and chloride ions. The solubility of silver chloride relies on there being space for the chloride ions to exist. And so we already have some chloride ions in existence, so we have to take that into account when we look at our equilibrium. So we're going to start by writing an equilibrium reaction for silver chloride. So AgCl solid, in equilibrium, it breaks apart into silver ion and chloride ion. And we're going to use an ice table to organize our information. We're going to ignore our silver chloride solid because it's not going to show up in our equilibrium expression. Now, to start with, we have no silver, and we don't have any chloride ion from the silver chloride, but we do have chloride ion from the sodium chloride. Specifically, we already have 0.55 molar chloride ion from the silver chloride because we have 0.55 molar sodium chloride dissolved. It is completely soluble, so we're going to end up with 0.55 molar sodium and 0.55 molar chlorine. So we already have some chloride ion in our solution. And we know when we add the silver chloride that we are going to increase our concentrations by some amount X because we have a coefficients of 1 for both our silver and our chloride. So at equilibrium, our silver concentration is going to be X. Our chloride concentration is going to be 0.55 plus X. So it already exists plus some amount X. So when we write our Ksp expression, we're going to look at the concentration of silver times the concentration of chlorine. And at equilibrium, this is X and 0.55 plus X. Now, we're going to simplify this a little bit because we know that silver chloride has a super low solubility. The Ksp is actually equal to 1.8 times 10 to the negative 10th. That's the Ksp value of silver chloride. So what we can rationalize is that very little chloride ion is going to come from the silver chloride. So we're going to say that this change here is essentially 0. So we end up with 0.55 X equals 1.8 times 10 to the negative 10th, which gets us X as being 3.3 times 10 to the negative 10th molar. So what we're going to do now is we are going to look at how that concentration relates back to the mass of silver chloride. So we know that we have our equilibrium concentration of silver is, I'm actually going to move this over. Our equilibrium concentration of silver is 3.3 times 10 to the negative 10th moles of silver ion in 1 liter. And we know that we have 1 mole of silver to every 1 mole of silver chloride, because it's a 1-to-1 ratio. And then 1 mole of silver chloride has a mass of 143.32 grams. So then this comes out to be, so our moles of silver cancels, moles of silver chloride, and we end up with grams of silver chloride, and we get that 4.7 times 10 to the negative 8th grams of silver chloride dissolve in 1 liter. So that answers our question, what mass of silver chloride will dissolve? Not a whole lot is what it turns out to be. So this question is asking us to look at the solubility of silver chromate in a solution of potassium chromate. So our common ion is going to be the chromate ion. So our solubility reaction for silver chromate is silver chromate, so Ag2CrO4, solid, breaking apart into its 2 ions. So we get 2 silver ions, and we get 1 chromate ion. And then we're going to use an ice table to set up and organize our information. So we know we're not going to include the solid in our equilibrium expression, so we're not going to worry about that. Initially, we have no silver in this solution, and initially we have 0.005 molar chromate, because we have 0.005 molar potassium chromate. There's 1 chromate ion for every 1 potassium chromate particle, and so that is a 1-to-1 ratio for the concentration. So that's the existing amount of chromate ion. Our change, we are going to increase by 2x for our silver ion concentration, because it has a 2 coefficient, and we're going to increase by x for our chromate ion because it has a 1 coefficient. So at equilibrium, our concentration of silver ion will be 2x, and at equilibrium, our chromate ion will be 0.005 plus x. Okay, and then when we look at our Ksp, our expression would be silver ion, well, we're given it in the question, so it's silver ion squared times our chromate ion concentration, which would be 2x squared times 0.005 plus x. And then that is equal to 9 times 10 to the negative 12th. So we can simplify this a little bit by acknowledging that our silver chromate is very non-soluble, and so this change in concentration of chromate ion is going to be essentially 0. So that simplifies this to 4x squared times 0.005 equals 9 times 10 to the negative 12th, which gets me 4.5 times 10 to the negative 10th equals x squared, and take the square root, and we end up with x as a value of 2.1 times 10 to the negative 5th molar. Now we want to know the solubility of silver chromate. So we know at equilibrium, our concentration of silver, is going to be 2 times x. So 2 times 2.1 times 10 to the negative fifth, which gets me 4.2 times 10 to the negative fifth molar. And then my ratio of silver to silver chromate, so this is silver ion, and we know that there are 2 silver ions for every 1 silver chromate. So then I end up back at 2.1 times 10 to the negative fifth molar for my concentration of silver chromate. So that would be the solubility in the potassium chromate solution. Now we're told in the question the solubility of silver chromate in pure water. If there's a common ion, our solubility should be less, which in this case it is. The concentration is lower than the concentration in pure water, so logically our answer makes sense.